So here I'm going to list all the ingredients or elements. For isotropic and kinematic. Hard. So the first ingredient is the additive decomposition. In a stream. So we have this total strain rate, which can be decomposed into an elastic part and a plastic part. This is the first ingredient that we have. The second ingredient is Hooke's law. So the original Hooke's law is that sigma, let's talk about rates, is equal to the Young modulus times the strain rate. But since we already know this, we can express this in terms of the additive decomposition. This is the second ingredient we have. A third ingredient is the so-called flow rule. So anyone that remembers this one. Equal to dq d sigma. Or this is called the plastic multiplier. And this Q is called plastic potential. And what happens when Q is equal to F, where F is the yield function? How do we call it? When Q is equal to F. Associative plasticity. So this is associative flow rule. What else? Lambda dot, or the plastic multiplier, is equal to what? This is positive, right? Greater or equal to 1, and equal to the norm of this guy. So this is the norm of the plastic strain rate. This derivative, in general, will give us direction. Since it will tell us whether or not we are in tension or compression. So the fourth ingredient is the hardening law. And here we have two different cases. One is for the isotropic hardening, where this sigma dot is equal to sigma y dot, and this is equal to H prime absolute value of the plastic strain rate. Which implies that sine sigma is equal to sine of H prime. We can also express this one as sigma y dot equals to H prime lambda. This is the isotropic hardening. The case for the kinematic hardening would be sigma dot is equal to sigma y dot equals to H prime, but not the absolute value, but the total value of plastic strain. And remember that we can express this as lambda dot df the sigma here. So we have H prime lambda dot df and we call it gamma dot, which is a new classic multiplier.
Is that a sigma dot? The sign?
This one?
Yeah.
Oh, no, sigma.
Okay.
The sign of sigma equals to sign of H prime. And with the consistency condition, we'll prove that this is equal to alpha dot, where this alpha, as you may remember, is the back stress in the kinematic current. So we have another ingredient, which is the consistency condition. As you already know, is F dot being equal to 0. Now we can express F dot, F as a function of sigma and this C, which is a plastic internal variable. It's just like plastic internal variable. So for instance, in the case of isotropic hardening, which is this one? Sigma y. And for kinematic hardening, alpha. Right? And we can express or rewrite this consistency condition using the chain rule or total derivative in terms of sigma and in terms of this C plastic internal variable. So for instance, for isotropic hardening, we know that F is equals to sigma minus sigma y, right? So the sigma will be sine of sigma dot, the C, which in this case is sigma y, will be minus 1 sigma y minus sigma y dot. This is equal to 0. But we know this guy from Hooke's law here. So sigma dot sine of and this sigma y dot we know from the hardening law, which is H prime lambda dot is equal to 0.
The sine of sigma times the E epsilon dot minus epsilon P.
Mm-hmm. Sine of, oh, sorry, sine of sigma. Right. So I'm working out this expression and collecting terms, isolating lambda dot, we arrive to an expression for lambda dot for the plastic multiplier, which is sine of sigma Young modulus E plus H prime E dot. This for isotropic hardening. In the case of kinematic hardening, we have that F is equal to F. Absolute value of sigma minus alpha minus sigma y naught. So following the same procedure, here we arrive to a similar expression. But instead we have sine of sigma minus alpha, the back stress. That's the only difference. And this one is for kinematic hardening. So in general, for two cases, or for a general case, we can express lambda dot as a function of this derivative times p divided by p as h prime dot. Which implies that plastic strain rate is equal to this quantity here. But we know that sigma dot is equal to E minus plastic dot. So substituting this into this, back into this expression, we arrive where this constant here is what? ET. Tangible. This is ET. Very careful. Any questions? So finally, let's give a geometrical interpretation to the models. So on one hand, we have isotropic, where in this case we have one dimensional space in terms of a stress. And this this is the direction of loading. So this is the original elastic region. So if we move here, this is sigma y, which can be computed as equals to a parameter times sigma y naught, where this beta parameter is equal, greater or equal than 1. And it moves by the same amount here to the negative direction. And this here is the new elastic field. So the norm or the length of this elastic region is sigma y minus sigma y, which gives us 2 sigma y. We can express it in terms of this parameter and sigma y naught, which will give us 2 beta sigma y naught. Kinematic hardening, we can draw a similar figure. But when we move the load towards this point, sigma y can be also expressed in traction. Sigma y in traction can also be expressed in terms of this parameter and sigma y naught. But in this case, this here will move by the same amount. So this is sigma y for compression. which is equal to minus sigma y naught plus beta sigma y naught minus sigma y naught, which gives us beta minus 2 sigma y naught. Is that right? Well, this is greater or equal to 1. And the length of the elastic region would be what? Sigma y in tension minus sigma y compression, which gives us beta sigma y naught minus beta minus 2 sigma y naught, which is 2 sigma y naught, which is also the length of the original elastic region that is supposed to happen in the magnetic current. That's it. Those are all the ingredients that we have for 1D bilinear plasticity, isotropic and kinematic. So with that, we can now proceed to integrate the same elements in a numerical sense. So let's begin with isotropic hardening again. And the first ingredient was which one? Number 1 is additive position, right? So remember the original is this is the analytical, the theoretical one. And a discrete form can be expressed into this way. Since we can write, for instance, epsilon dot equal to delta epsilon delta t, right? Do the same thing for all of them, so we have all the delta t's gone. And we end up with this expression. The second ingredient, which is Hooke's law, in terms of the additive decomposition, the original form is this one, and the discrete form will be delta sigma equals to delta epsilon minus delta ep. Right. But we can express this delta sigma express this delta sigma as sigma n plus 1 minus sigma n, where sigma n is sigma at Tn. Tn is a discrete time maybe it is also a useful thing. For instance, if I have to integrate this, right, this is equal to x at Tn plus 1, Tn plus 1 minus x of Tn. So that is delta x. So this and this here, combining the two of them, we can rewrite that expression. Sigma n plus 1 equals to sigma n plus E delta epsilon minus E delta epsilon P, where this is the so-called elastic predictor, and this is the plastic correction. We also call this whole elastic predictor sigma n plus 1 trial. So Hooke's law can be written like sigma n plus 1 is equal to sigma n plus 1 trial minus plastic corrector. And this is the discrete form. The third ingredient is right? So the original form is the plastic return rate equal to plastic multiplier df is sigma. The same way we can go delta epsilon plastic equal to delta lambda df is sigma. But here we have to make a choice. We have to decide where to evaluate this derivative in time. So for instance, if we choose t m plus 1, that would make this an implicit method. And we'll be using backward Euler. Right? But if we choose it to be Tn, that will be forward Euler. Are you guys familiar with that? Finite difference schemes?
Yeah, but I thought it was the other way. I thought backward Euler was explicit. I don't know.
No. Backward Euler is always implicit. Forward Euler is the one that you depart from something that you know to complete something that you don't know. In this case, you don't know this guy, and you don't know the guy here. Well, the part, this is n plus 1. So you don't know this. And this, we know this is sine of sigma n plus 1. That we can already also show that this sine of sigma n plus 1 is equal to sine of sigma n plus 1 trial. So this whole thing will be delta epsilon plastic equal to delta gamma sine of sigma n plus 1 trial. Foreign ingredient was the hardening law. So for isotropic, we had that sigma y dot is equal to h prime lambda dot. So delta sigma y equal to h prime delta lambda. So sigma y n plus 1 is equal to sigma y n plus h prime delta lambda. The last ingredient was number 5. It was consistency condition. But here we actually use only the gel food. At yielding in plasticity. So for isotropic hardening, the yield function sigma is nothing but the absolute value of sigma minus sigma y. Right? So this yield function in its discrete form can be written like that. Since we're assuming plasticity is equal to 0. We can express this one as a sine of sigma n plus 1, right, times sigma n plus 1 minus sigma y n plus 1 equals 0. But we already have this result here. So sigma, the sine of sigma n plus 1 trial can be put here instead of the original one. And sigma n plus 1 we already know from the Hooke's law, from the discrete Hooke's law, which is sigma n plus 1 trial, right, minus the plastic corrector, which was E delta lambda, right? Minus, we also know this guy here, sigma yn minus h prime delta lambda. This is equal to 0. And collecting terms and so on and so forth, we write an expression for delta lambda, which is the absolute value of sigma n plus 1 trial minus sigma yn divided by h prime plus e. This is the expression to compute the discrete plastic multiplier, or the discrete version of the plastic multiplier. So, if you remember the analytical version of the plastic multiplier, I'm going to just put back here to make a comparison. Sine sigma is this one, right? So they are different. They come from different parts. And that's why we have to get this in general for all the theory of plasticity, 3 dimensions, 2 dimensions. We have to compute it if we want a proper convergence. We can also use this one, but we won't get the same rate of convergence as using the proper one. And this is painful for more dimensions. So, folks like this are written just to compute these parameters in the implicit version of the method. So finally, the nice geometric interpretation of this predictor corrector model. what this thing does is, once we go into plasticity, the predictor part takes, as you remember, sigma m plus 1 is equal to sigma m plus 1 trial minus epsilon delta lambda. So this here is E delta lambda. It takes, we already know sigma n, so it predicts that the following step is elastic. So it departs from sigma n and takes it to an elastic step. And then it realizes that we are actually in plasticity. And then it comes back to the yield surface here, like this. So it predicts every next step as an elastic step. But once it realizes that this is plastic, that this value is bigger than the actual yield function, it corrects and brings the value to the yield surface, making it 0. Sorry, this is and this is true. Right. Questions? No. So that's it for the isotropic mode. That's the whole integration of the isotropic mode. Once we get this guy, we can compute every other parameter or variable that we want. And now, let's proceed with the kinematic curve. Again, same ingredients. We already know that one is the additive decomposition. So delta epsilon equals delta epsilon T plus delta epsilon T, the discrete. The second ingredient is Hooke's law. We already know version of that is sigma m plus 1 is equal to sigma m plus 1 trial minus T delta epsilon T. The third ingredient is the flow rule. And here we have something different. So the original one in the analytical form is this one. And what changes here It's just this derivative. What will be this derivative in this case? Minus alpha, and that's it. So it is delta epsilon p equals delta lambda sine sigma n plus 1 minus alpha n plus 1. But it can be also shown that this sine is equal to sine of sigma n plus 1 trial minus alpha at Tn. So this is equal to that. And geometrically, it's very simple to understand this. So this will be expression for the kinematic current of the discrete expression. The fourth ingredient is the hardening law, which was also different in this case. So we had that alpha dot was equal to this gamma dot, right? Df is sigma. But this gamma dot was equal to what? H prime lambda dot. And this for the kinematic hardening, again, this one, sine sigma minus alpha. So the discrete version is nothing but alpha at time n plus 1 equal to alpha at time n plus h prime delta lambda sine of sigma n plus 1 trial minus alpha at time n.
Just to make sure it's alpha n up there, right? Not n plus 1.
Whatever. Oh, here.
In the box answer.
Here.
Yeah.
This is n.
Alpha n, okay.
This is equal to that.
Okay.
And the last element is the consistency condition. Once again, we only need to use the yield surface itself at yielding plasticity. So in this case, the original yield surface is the absolute value of sigma minus alpha minus sigma y naught. Since we're at plasticity, this is equal to 0. The discrete version will be sigma n plus 1, let's say, sine sigma n plus 1 trial minus alpha m, right, multiplied by sigma m plus 1 minus alpha m plus 1, and this minus sigma y not equal to 0. Once again, we know these guys. We know this guy from Hooke's law here, and we know this term from here. So we replace those in this expression, collect terms, and isolate delta lambda again. Doing that, we arrive to delta lambda equal to absolute value sigma trial n plus 1 minus alpha n sigma y naught divided by h prime plus e. And this one is also different from the analytical one. So when sigma m plus 1 trial minus alpha m is bigger than sigma y naught, that means we're in plasticity, and then we send the algorithm to correct and go back to the Jerves surface. Otherwise, it is an elastic step, and this is 0. Any questions?
Can you please repeat what you just said here?
Here.
Yeah.
So this is the numerator, right? So it has to be, this is, in general, delta lambda has to be positive or 0, right? So when we compute it in your code, you go and make your own code. And if, for instance, this one is negative, that means nothing but an elastic step. This is 0, we have nothing to correct. We are on the yellow surface. And when this is bigger than 0, then we are in fact in plasticity. And what the algorithm is doing is sending the predictor and is doing this. So we have to correct. Finally, the corresponding geometric interpretation. everything is the same, but something is different. Here, we have that since this is kinematic hardening, we have to remain with the same original elastic region. So if we move from this point to that point here, this is going to be alpha, right? Actually, this is alpha n plus 1. So here we have something that let's exaggerate a little bit. Alpha n. With the same slope as this one. And from a previous time step, we have here alpha. Right. So this has to be sigma y naught all the time.
Shouldn't alpha n be 0 until you hit plasticity?
Here,
The
here is 0, here no.
the line below then, so I'm confused with the alpha n.
Oh, this is the time step n, right?
Sorry, I meant the line you drew.
This one?
Yeah.
Oh, okay.
Confused by that.
If
What
you
is-
want me to, maybe it is kind of confusing. So what I'm trying to say is that at this time step, we already know alpha n plus 1, which is the one that we're going to use here, right? To compute this guy here, we're going to use this one right here. So we use the one coming from the previous time step to compute the new one. That's what I'm trying to say.
Why shouldn't it be alpha?
It is alpha n. What I'm trying to say with it is that we will use it here
Oh.
to correct this. Because once you are like yielding in kinematic hardening, you're pushing your surface, right? And for the new time step, you have to use the previous yielding point,
Yes.
right? So that's what I'm trying to say with that.
Oh, okay.
To compute a new one, I have to use the previous yielding point.
But what's the slope of the line mean then? That's
Oh, that's how this thing is going to be increasing. Because this is going to have the same slope as this one. Remember that alpha dot is equal to sigma dot, right? From the consistency condition. So this one is going to have the same slope.
But how come here the things start at like 0?
It starts at 0.
Wait.
Oh, okay, well, here,
Should
it
be
starts
zero.
at 0 here. Yeah,
Okay.
sorry.
okay.
Yeah, you guys are right. Yeah, that's misleading. So, like that.
But then the equation you wrote with alpha dot is equal to sigma dot is not. Because where it has it's only an increment in plasticity.
In plasticity,
Right.
only in plasticity, not before.
Uh-huh.
It only goes for plasticity.
No. Okay.
Any questions? So all of this corresponds to sections 2.8 and 2.9 in this book. So if you guys want to go and read and know more, and if you want to get a bigger picture of these kind of algorithms, you can see this book. By Simon Hughes. This is the I guess, one of the best books in this subject. And that will be it today.